Good morning. How are you doing? I'm Mr. Ish. Thank you for joining me. We're looking here at a pH comparison calculation between a strong acid and a weak acid. And this right here is not a simple dilution exercise by any means. We have strong acid, weak acid, hydrochloric acid, and acetic acid, ACA, acetic acid. We have 0.02 molar HCl 600 ml. This has a certain pH, but it must be equal in pH to this. What must the molarity of acetic acid be? 600 milliliters of it. So both of these pH values are the same. And how would you go about doing it? Again, we're looking at a certain molarity of the weak acid such that it would have the same pH as the strong acid. You would start by determining the pH of the strong acid, and you know your HCl, which is a very strong acid, would dissociate 100% into something like that. There's no point in you doing start, change, and end, but you can, just for confidence reasons. This 0.02 molar is exactly everything which you can feed right through. You have 0.02 molar of it, you have 0, but after the dissociation, because we know it dissociates 100%, you're going to have 0.02 subtracting and you'll have 0.02 adding over here. What you'll end up seeing is this zeroes out, HCl zeroes out because it dissociates completely into these aqueous ions. Your amount of hydrogen ion concentration is 0.02 molar. pH is equal to negative log H plus. You can see here the volume here was irrelevant for this calculation, but you can do it minus log 0.02 and you can take that through. It's not difficult. You'll do 0.02 log and minus 1.699. I'll round it up. This has a pH of 1.699. What must be the molarity of acetic acid? 600 ml of it, so it would also have a pH 1.699. Now you'll see the significance of the difference in terms of the molarity of a weak acid and a hydrochloric acid by means of this calculation. Your acetic acid has a certain molarity. We don't know what it is, but we know with regards to its volume, it has a pH now of 1.699. What is that molarity? Well, do your acetic acid representation as HA. You know, acetic acid is CH3, C double bond OH. We're not going to write it out as that, we'll just write it out as HA. That's my acid. Plus, in presence of water, it partially ionizes, hence the double arrows. You'll have a conjugate base and then you'll have your conjugate acid. You don't know how much of this we have, but we have start, change, and end. What we will feed over here won't be the molarities, it'll be the moles. Molarity is equal to mole over volume. Mole is equal to mv. I have a certain m molarity, I'll call that y. I have a certain volume, 600 ml. You convert that into liters, it's 0.6. So I have 0.6 y. Volume times an unknown molarity. I have 0, I'll have minus x. Why is this minus x? Because this will be placed into a solution, it will dissociate a bit, and these items here will rise in quantity. You have an x, you have a 0.6 y minus x. Imagine if this acetic acid has a 1.8 times 10 to the minus 5 acid dissociation constant, because that'll come into play. You'll write the Ka. Ka, your acid dissociation constant, is equal to this times that, x times x divided by 0.6 y minus x, which is equal to your acid dissociation constant, 1.8 times 10 to the minus 5. Because this acid dissociation constant is small, you can literally cancel out that x minus x. What you're looking here at x squared is equal to, you see 0.6 y multiplying across, you can take this 0.6 and multiply it across. You have 1.8 exponent 5 minus times 0.6. I'm getting 1.08 times 10 to the minus 5. X squared is equal to 1.08 times 10 to the minus 5, but y. X, which is equal to here your hydronium ion concentration, which is the same thing as hydrogen ion, is equal to the square root of all that, 1.08 times 10 to the minus 5y. That right there will drive everything now. You don't need to see this equilibrium calculation, none of that, because you've seen it. I'm going to erase it to finish the question for you. We know the pH of this weak acid is 1.699. We don't know its molarity, but the y value, the y variable, represents the molarity. How can we do that? Well, how about this? We solve for y using an equation. We know pH is equal to negative log H plus. I know what my this thing is. It's that entire expression. I know what this right here is. It's 1.699 is equal to negative log My hydrogen ion concentration is 1.08 times 10 to the minus 5 y. I'm going to calculate for that y. The first thing I'm going to do is I'm going to take the minus on the other side, then I'll take the log on the other side. You'll be looking at 10 to the power of minus 1.699. Remember, when you take the log on the other side, you're bringing in the exponential base 10, because the log on your calculator default is a base 10. Log always base 10. So let's do that. We have 1.699. I'm taking the minus on the other side, then I'm shifting the log and I'm bringing in the exponential base 10. I have 0.01999. I won't actually do anything with that, but I know it's equal to square root of 1.08 times 10 to the minus 5y. And now I'm going to take this square root on the other side and it's going to become a square. I have the value already. I'm going to square it because the square root on the other side of the equal sign is a square. An exponent, I have 3.99 times 10 to the minus 4. I have 3.99 times 10 to the minus 4 is equal to this. 1.08 times 10 to the minus 5y, and y is equal to, you take this and you divide it on the other side. I have 3.99 exponent 4 minus divided by your 1.08 exponent 5 minus, and we have a y value here of 37. What is 37? 37 tells us it's our molars. 37 molarity or 37 molars of acetic acid. 600 ml will give you a pH of 1.699, and your answer has been solved. Your question is complete. We had this expression over here. I had 1.699 is equal to minus log all of this. I took the minus on the other side, then I took the log on the other side. I have this 10 exponent minus 1.699. I took the square root on that side, you're squaring it all. Then I'm taking this value on the other side, you're dividing it, and you're getting a y value. 37 molar represents a highly concentrated solution. You know, molarity is equal to moles over volume, but moles is equal to mass over molecular weight. If you know now the molarity times the volume, you can determine how much acetic acid you're dissolving in liquid. Acetic acid has a molar mass of 60 grams per mole. I have 37 molar times volume 0.6 times 60 grams per mole. What am I doing here? I'm determining the mass. Well, I don't have to do it. The question is not asking, but I'm doing it for a little perspective. 37 molars times 0.6, which is your liters. That right there is your moles of acetic acid multiplied by its molecular weight 60. I'm adding in 1332 grams of acetic acid and 600 ml of water to get this concentrated, super concentrated solution. Of course, I'm not worrying too much about density. There would be a little bit of a variance with regards to the density coming into play, but your amount of dissolving would be somewhere close to 1332 grams of acetic acid dissolved in 600 milliliters of water. It will generate a pH solution which is 1.699, and your answer is gut.